Hey, how you doing? Hey, so I want to talk a little while about polarity of wall outlets. Specifically, what I want to talk about today are these types of outlets. They can come in either a single device on a yoke or two devices on a yoke. This would be called a duplex receptacle here. And proper polarity and why that matters. This type of device is something that we're all pretty used to, right? Anybody is familiar with this type of device. It might look different in different countries, but this is the standard device type that you'll see in the United States. This one happens to be a 15 amp device, which you can tell because it has the ground, which is this bottom rounded opening, and then it has these two parallel ports, the shorter one on the right being the hot leg and the longer one on the left being for the neutral connection. This one being 15 amp would look like this. If this were 20 amps, it would have another little line that is parallel off of this left side that would indicate that it is a 20 amp rated device. This one's 15. You could watch do-it-yourself videos. I'm sure you might learn enough from this video to make the wiring connections to a duplex receptacle and feel pretty confident that it's going to work. And it's fairly simple to do, but if you mess it up, then it can be quite dangerous if you reverse polarity on a device such as this. And even though sometimes, even if you reverse polarity, the device will work, it does create safety concerns. And so we're going to talk about that in this video. So I've got a few different things here that I gathered from around my house that I wanted to show y'all. So first thing, there's this skill saw here. This skill saw is a double insulated tool. And there's this symbol, it's like a small square inside of a larger square, indicates that it's double insulated. And this tool is built in a way to minimize the potential of electrocution. It would be very hard to get electrocuted off of a tool that's double insulated. So the outside, you can see that everything on the outside is plastic. I took some continuity readings earlier to see if there was any sort of electrical connection from the exposed metal parts to either of the prongs in this plug, and there aren't any. So all the metal parts, everything about metallic and conductive about this tool is electrically isolated, and all of the parts that I'm coming in contact with are plastic or electrically isolated so that I can't get electrocuted off of the use of this tool. And a double insulated tool will have a two-pronged device such as this, as opposed to this fan that I have, which is a three-pronged device. So something to note on this two-pronged device, you can see that this side here is not as wide as the side on this opposite side. That indicates that there is a polarity to this. There's a direction that matters the way I plug it in. And so the left-hand side here being neutral. And you can see that it fits in to that plug that way. But if I try to turn it around, it will not fit in that plug. I can't go put it in. So the polarity of this device matters. We don't want to get that backwards. So that's this device. That's a double insulated tool. I have also a lamp from my house here. This also has two prongs. It's a little bent. We've had this for many years. But this also is the same way, where the left-hand side is larger than the right. I can plug it in one way, but I can't plug it in the other. And with this lamp, I can demonstrate, this is not double insulated, but I can demonstrate to you what one of the risks would be if we were to wire this device backwards to where the polarity of this being plugged in was not per design. Because per design, the larger plug side of this plug should be connected to neutral. The smaller side should be connected to hot. And that's very important. So we're all familiar with a light bulb. Light bulb has two contact points on it for the electrical circuit. You have the point on the bottom, a very small point on the very bottom. That's where your hot connection is being made. Line 1, line 2, line 3, your hot wire. And then the outside ring, this is your neutral connection. You can see how much more surface area there is. Also inside the socket, you can see that the point that is hot is very deep inside the socket, whereas the larger outer ring is the neutral. Now the reason that matters is that whether or not you know, but neutral does carry current. It's part of the circuit. There is voltage potential between neutral and hot, but between neutral and ground, in a properly installed electrical circuit, there is no potential difference. Sometimes you might have a volt potential difference, and there are reasons for that, but it's very, very low, if any, potential difference between neutral and ground. So why does that matter? Well, since there's low potential between neutral and ground, then I can come in contact. I can usually make physical contact with the neutral conductor and not get an electrical shock out of that. Now, if this device were to be wired with reverse polarity, that meaning that when this device was installed, that instead the hot conductor was wired to the neutral side and vice versa, the neutral was connected to the hot side, then what would happen is that this outer shell and this part of the lamp that has a large surface area of metal would then become energized with a potential difference. So that if I were screwing this in, I'm screwing this in, and if I were to, or even taking it out, and I were to come in contact with that large surface area of metal, which there's a high potential for that to happen, and I were also grounded somewhere else on my body, then I would get an electric shock. And so that would be the hazard. So I want to show you with my continuity meter just to prove that, just to prove the way this is wired. So as I said earlier, the larger side is the neutral, so I'm going to take my meter here, connect that to neutral, and then I'm going to touch the outside of this here lamp, and you can hear that I have a tone there. So that's telling me there's a connection between this neutral and the outer shell. Okay? It's also important when you're installing the end plug on this that you know which conductor on this jacket is the neutral conductor connected to this shell. And that's going to be the identified conductor. Same thing with this. The identified side is the side that is larger than the rest. That would be considered identified. On this cable, when I feel it, on the hot conductor side is smooth. The neutral conductor side has kind of a rib on it. Okay, so then that will tell me that, then once I feel that and I realize that, I can say, okay, that's my neutral wire. The side that's ribbed has texture to it. Sometimes there's lettering on it, and so the side with lettering on it, that would be your neutral side, and then the unidentified side would be your hot, and that's how you would identify these conductors in a clear cable like that in order to make that termination. Okay, so that's those types of two-pronged receptacle plug connectors. I'm gonna go to this fan. The knees sitting on the ground here trying to show you all this. So with this fan, now I have a three-pronged device. Okay, so this is still a polarized device. But something you'll notice about this is the two parallel prongs here are the same size. So the thing about this plug that forces the polarity connection is the presence of this ground. A lot of times you might have an extension cord that the ground has been broken off on. What's very dangerous about that is that once that ground is broken off, now it can get plugged in both directions, and you could get reverse polarity out of that. And in the field, when we're working in the field, and if you have a table saw, and maybe that also had the ground broken off, or you have double insulated tools where the insulation on that tool has been damaged, and now the worker is exposed to risk, and now you have reverse polarity. That's why we need to be replacing those cord caps with a grounded cord cap, because not only are you no longer grounded without that, but also there's a risk of polarity, of devices being connected out of polarity. Okay, so keep an eye out for that on your job sites and make sure that that's getting taken care of. So we've got this fan here, three-pronged device. So that means it has an equipment ground connection, a neutral connection, and a hot connection. Now let's see what we have. If we have any connection between neutral and ground, and we shouldn't, so I'm just going to confirm that. So we don't. Okay, now I'm going to go to the metal here. Okay, so neutral, I'm confirming right now that my cord is good and I don't have any shorts between neutral and ground, so I don't have any. Now I'm going to take my prong to the ground lead here, and now touch the fan, and so the fan is grounded. So if I plug this in to a grounded device, then the fan will be grounded, and that's exactly what I want. Now what would happen if I reversed the hot and the ground in my connection in this? Well, that would be really bad, wouldn't it? Because what would happen then is I would have a grounded connection on this terminal, but if this device wasn't wired right, and instead we had a hot conductor going to ground, then the entire shell of this fan would become energized, right? Because it's grounded, right? So this brings me to the whole point of making this video. Now, where did I put my tool? No, sit on it. Okay. So the whole point of this video is to make sure that as electricians that we are doing what we are responsible to do. Our responsibility is to install an electrically safe, is to provide an electrically safe installation that anybody, the end user, can go plug it in and be safe and know that they're not going to get electrocuted, that the building's not going to burn down, all that. That's our entire job. So this here tool is something we all should have, and we all should be doing at the end of our project something called a hot check. Well, a lot of us are very confident in our abilities and all that. It's like, yeah, no, I know I wired it right. Okay, but you don't know you wired it right until you tested and verified that it is right. Something could have happened. Somebody else on the crew, maybe they made up a junction box wrong. Maybe it was dark in the room and the green and the black looked very similar and they were landed on the device backwards. And I've seen this happen before. And then what ends up happening is that the entire shell of the equipment that's attached then becomes energized and is an electrocution hazard, just waiting for somebody to come and complete that circuit and then get electrocuted. So whenever we put any electrical equipment into service, we have to do a hot check. And with these types of devices, the way we do that is with one of these. I'll show you how to do it with a volt tester also, but this really is the most efficient tool to do that with. So on this tool, you can see that there are a lot of different indicators on there for what faults you might read or whether or not it is wired correctly. So when you have one of these, I'm holding that upside down. So when you have one of these, take a look at that. I don't have it memorized. I just know that when the lights don't show the way they're supposed to be, then I'll look and I'll see what the problem is. And it's a very quick troubleshooting tool. So if I plug this in here, what I see, I'm very familiar with these lights and I know that this is a correctly wired device. That the outside light is not lit. This red one on the very left, the one in the middle is lit, and the one on the right is lit. Any other combination of lit or not lit lights here will indicate that this device is not wired correctly. We need to take it out of service, repair whatever is wrong, and then we can return it to service, check again, and if it's good to go, then you can let the customer use it. You can release it for use as temporary power on the job, whatever the situation is. And that's what you would do with receptacles. And you need to do with lighting, you need to confirm that the lighting works, the emergency ballast works, the exit lights work when you turn the power off, things are wired to the right circuit, your three-ways work, your GFCI receptacles work. If you don't have a good system for how you're going to go through this and confirm that everything has been checked and is working, then come up with one. This is a very important step. And when, in this economy of everything's fast and there's not enough skilled labor to get everything done, we're all very rushed, and this might be a step that you like, I know it works, I'm going to get out of here. But you're running the risk of maybe something's not working right, and maybe something is actually wired dangerously and needs to be addressed. And you won't know because you never checked it. So very important step to take. Don't skip this step. Make sure it happens. Okay, so what I'm gonna do next is I want to, kind of deciding if I want to do this. What I was gonna do was actually wire this out of polarity so that you could see the lights be different. And actually, I'm gonna do that. So bear with me. I'm at my home. I have arc fault devices in my house. This is a GFCI tester. Arc fault devices are also GFCE devices. It's pretty common in residential that they don't make pigtails on their devices. With commercial work, we always put pigtails on our devices. I think maybe the reason why is because in commercial work, we're more prone to installing multi-wire branch circuits. And there are some rules when you do install a multi-wire branch circuit that you can't terminate your neutrals on a device to where if I open this circuit up, it would then create an open neutral condition downstream. So that's why, and I think multi-wire branch circuits are not as common in residential, so you won't see that. So whereas in this device in my home, where this neutral was landed on this device, which is actually a fine installation, it's gonna work all day, and it's not gonna cause any hazards because this is not a multi-wire branch circuit. In other words, you don't have A phase, B phase, or in other terms, line 1, line 2, sharing a neutral. So if I had that, line 1, line 2 sharing a neutral, and I only turned off the circuit for line 1, and then I come and I take this device apart, well, now I have an open neutral condition on line 2, and that could cause some voltage imbalances in the circuit depending on what loads are connected. And so when you have multi-wire branch circuits, you cannot terminate them in this manner. This would then be illegal. It's not illegal here, but in that situation. So because multi-wire branch circuits are much more common in commercial and industrial work, a little less as time goes on. It's a practice we're starting to do less and less of. Then that's probably why in that environment we don't do this and we put pigtails on everything. In residential, I like to tuck the ground in the back first because it's a bare conductor, and since it's a bare conductor, not like bears, like in the wild, but bare, like not insulated. If you tuck that in the back first, there's less of a chance that it will short out against the terminals on the device. The correct way to wire this device is you have brass screws, brass color screws. Some devices that might be black. I think devices that are weather resistant rated, that brass screw is actually black. And then you have silver screws and your ground screws. And on these devices, your silver screws and your ground screws. Let me go backwards and say what they actually represent. So you have brass screws, which could also be black. Those represent where your hot conductor goes. Your line 1, your line 2, it's typically going to be a black, red, blue, of some type of color is what will terminate here on that brass screw. On the silver screw, that's our neutral conductor, and that's going to be this white conductor. That's your neutral conductor. And then your ground conductor being green, that's your equipment ground conductor. That's in your home, that's usually going to be bare. In a commercial or industrial environment, that's going to be insulated green typically. It usually won't be bare. That's what I mean by typically. So that's the correct polarity. Any landing in any other way will be out of polarity. So what I'm going to actually do, I'm going to wire this out of polarity so that I can demonstrate what happens on the outside of this fan when wired backwards. I'm in my house, so it might not actually let me do it because I have arc fault breakers, so it might realize that there's a problem and trip on its own. But I want you to see how dangerous this is to wire backwards. Okay, so the camera overheated. The one thing I'm learning to make these videos, and I bought this GoPro 10 I don't know why I thought GoPro would be a good camera. They're action cameras. They're meant to be riding your bike and a lot of movement and air running across them. And the one I got, I'm doing all this stationary video and it just overheats. So I lost a little bit of this video, but hopefully I can figure out where I left off and pick it up. So, okay, so where I was at, I believe, was we were testing this fan. And what I had shown you was, and we'll do it again, was that we have this 3-prong device, and the long lower rounded prong represents the ground, and that we have from ground, I've got to put this on the right function so you can hear a tone, and so that we have continuity. You can hear that ringing. We have continuity now between our ground and the shell, and that's correct. Now if this device is incorrectly wired, then there's a potential that we could actually energize this entire shell of this piece of equipment. So I've actually incorrectly wired this on purpose, and now because it's incorrectly wired, I know that the outer prongs of this device are energized, so I do not want to touch them. I'll be very careful not to do that as I plug this in. And that what I can see now is that I have a different set of lights lit here. And this set of lights indicates that hot and ground has been reversed on this device. And this is very dangerous. And we're going to show you why this is very dangerous. So what I have now is 120 volts of potential voltage between this metal cage and anything grounded. Okay, so what we can see on this tester then is that we have a different set of lights that are lit. I have the outside red light lit, and I have the other outside orange light lit. It should be the 2 orange lights, the middle and this right side lit. So what this indicates is that hot and ground are reversed, which I know because I intentionally wired this wrong to show you guys. So what's happened now? What's happened, you can't see it, voltage is invisible, but this entire metal cage of this fan here is now energized. I have potential voltage between that exterior metal, and anything else that's grounded. So I'm going to take a lead to the grounded terminal here, and then to the cage, and I have 120 volts, 121.5 volts of potential. So that means if this has been turned over to me, if I'm the customer and this has been released to me, I'm going to plug in my appliance assuming that it's wired right. And I should have the confidence that this has been wired by a professional, and then I'm going to be safe. And I'm going to walk up to the fan and I'm going to put my hand on it and I'm going to try to turn it on. And heaven forbid, if any other part of my body is grounded to where I can complete a circuit, I'm going to have 120 volts running through my body. So that's a very serious electrocution hazard, simply because 2 wires on this device were swapped and then it wasn't tested. So we have to test our equipment. Now this is something I noticed earlier. It's interesting to me how quickly this picked up this particular metal cage. Maybe because of the way it's constructed, the rounded metal, I don't know, maybe it's making the signal stronger. But I've got this set to non-contact voltage, so this is something that a lot of electricians have to indicate whether or not there is voltage present. And I'm picking up voltage here. I'm about a foot away, and it's already telling me. But this is, this is a very large piece of metal. A lot of it's round, so that electromagnetic field might be excited, might be magnified to some extent. I don't know. But anyway, this is indicating to me that that's hot. So this is very important. You can imagine, you're putting a piece of equipment into service, telling the customer it's good to go, and they hook up something like this, and then heaven forbid they get electrocuted, their pets get electrocuted. Maybe something malfunctions in the equipment because it's wired this way, and then it causes a fire. So this is a very important step that we do, guys. As electricians, our job is to provide a very safe installation, an installation that protects people and property. It boils down to that. That's our job as electricians, is to protect people and property from getting electrocuted or burning down. So know your job, hot check our devices, and let's get it done, guys. Thanks. Okay, so I wanted to show you guys one other way if you don't have one of these to do a polarity test at a duplex receptacle such as this. And I want to tell you guys, if you're out there doing electrical work without testing equipment, then that's, quite frankly, that's pretty irresponsible. So I want you guys all to go out there and get some testing equipment. You don't have to spend, $500 on a tester like this. You can get one for 40 bucks. If it's a real hardship for you guys to get a tester and you need one, talk to the companies you work for. Tell them, hey, I'm out here doing this work. I don't have a tester. Whatever your reasons are, doesn't matter. Just, you got to get one. You got to have this in your tool bag. You're going to do electrical work. You got to have a voltage tester. Unless you're just you're going to be an installer and you're not going to be energizing circuits. I guess then you don't really need one. But if you're involved in any part with the energized side of the industry, then you absolutely have to have one of these. So anyway, that's enough of my preaching. I'll show you how this works. So for this tester, I'm going to set it to voltage. Okay. And I don't know if this is going to show very well in the video. I hope so. But there's a few things that I know. If this is going to be wired right, I have my neutral here on the upper left. This is with the ground installed down. So in the upper left, I have my neutral. On the upper right, I have my hot. And on the bottom, I have my ground. So I should have voltage potential between hot and ground and hot and neutral. And I should have 0 or near 0 volts between neutral and ground. And so I can test for polarity by knowing those things. I don't know if I can turn my light on here. The light doesn't work on my tester. Okay, so first thing I'm going to do is test from between my hot and my neutral prong and see what I have. And I have 120 volts. So that's good. Now I'm going to test from hot to ground. And I should have 120 volts, which I do. So far, so good. Now the next one I'm going to do is test from neutral to ground. And I should have near 0 volts. And I have 6.6 millivolts. So that's good. So this tells me that this is wired correctly. If I had a reading of 120 volts between neutral and ground, then that would tell me that I have a reverse polarity on this device and I need to take a look at it and fix it. Okay? So if you don't have one of these, that's how you can do it with your voltage tester.